to the next speaker and panelist that brings a very important perspective around computer science and software engineering. It's an absolute pleasure to be introducing Harold Thimbleby. Harold Thimbleby is Sea Change Fellow in Digital Health based at Swansea University. And he's actually also an expert advisor to so many different organizations, whether the Royal College of Physicians, the World Health Organization's Patient Safety Network. It's a long list. I think I personally, being a software provider for collaboration on product development, Wikifactory, I'm particularly interested in what you're going to say today, Harold. So okay. Over to you.
Okay. Well, thank you very much, Christina. I'm going to start sharing my screen. Is that working? Yeah. So Ben and Josh, and for many people, the emphasis is, can you hear me? Can you hear me?
Perfect. Thank you.
Good. For lots of people, the emphasis is on how we make stuff that meets the regulatory requirements. I'm going to worry about in this little talk that the regulatory requirements are generally bad and they've been relaxed because of the pandemic urgency. And the question is, how do we help everybody do high quality work that's appropriate to whatever they're doing? And I'm going to give a couple of examples of software that is rather bad, and then I'm going to explore some ideas for helping. So here we go. So JamVent is an open source ventilator made by Imperial College, and they say it passes the UK medical device regulations. I wrote to them and said, where's the software? Like, all the photographs of the device have it connected to a laptop. So what software is it running? How do you get it to build, and so on? And they mailed me back and said, our software is still being spiffed up. And spiffed is a word that means, it's an informal word. It means make somebody look better, more positive. And it's not a word you talk about with software. And it rather betrays that the software behind this is not something that they're able to share, and it needs a lot of work. So something's going wrong. They think they're developing a high quality device, they're sharing it, they're very excited about it, and yet the software is not available and probably is in a pretty poor state. Okay, that's interesting. Right, here we go. Have you heard of Neil Ferguson and his model at Imperial College? The Telegraph, one of the British newspapers, said his Imperial model could be the most devastating software mistake of all time. And his software has informed British policy, American policy, and Swedish policy, to my knowledge. And I think this headline is going over the top. Neil Ferguson's software came up with the same results as a lot of other epidemiologists did. But when people looked at his software, they were all horrified. In fact, I came across it because I use Twitter, and Neil Ferguson tweeted, here's his tweet. I wrote the code, it's thousands of lines of undocumented C 13 years ago to model flu pandemics, right? So this is not how you write code to inform public policy for a COVID pandemic. Something very strange is going on. I'm writing a book on digital health, and this is one of the pictures from it. It's a little epidemiological model. It's very straightforward. You start off with a few people being infected, then lots of people get infected, you recover, and then it all dies out. And the software is very straightforward. Here it is. I documented it, and the documentation is a nice little outliner. It's really easy to do. So the question is, how can we help people like expert epidemiologists, hardware manufacturers, ventilator makers, and the rest of them, anaesthetists who are building ventilators? How can we help them improve the quality of the engineering they're doing? And how can we help them improve, in particular, the software quality? The problem is everybody can program, children can program, but to program well is really very difficult. So in some fields, you are required to do a risk analysis before you start. And if you want FDA or MHRA regulatory approval, you have to know what category or class your device is going to be in, because if it's going to be, say, PPE, you don't have to work so hard as if it's going to be something like a defibrillator. So in some areas, like nuclear power, you do a risk analysis and then you allocate safety integrity levels to what you're doing. And they're SIL 1 to SIL 4, SIL 4 being the highest level. And then it works roughly like this. You work out how often things are going to happen, and across the bottom, how severe they are. So if something has negligible severity and doesn't happen very often, it's down in the bottom left of this. But if it happens frequently and the consequences are catastrophic, it's up in the top right. And the diagram becomes perhaps a bit clearer if I colour it in like this. The redder it is, the more risky the problem is. So your risk analysis would work out, what am I doing and what SIL level do I allocate it? And then the higher the SIL level, the more careful and the more professional your development has to be. And for many systems, there are different SIL levels. I thought a good example would be Amazon. Probably SIL 0 is when you buy something. If you get sent the wrong product or you lose your money, Amazon can send you some more money. It's not a big deal. Whereas if Amazon lose your credit card details, there's a lot of fraud and identity theft, and that's higher up on the right, SIL 3 or SIL 4, depending. So when you develop software for Amazon, you may be anywhere on the spectrum. The same with medical software. Some of it is low level and some of it is very critical, but you need to do the risk analysis to know where you are. Most of the stuff we're trying to help with COVID is in this area. So if your 3D printing for PPE goes wrong, everything that is printed is going to be a mess. And the consequences of that is people will catch or infect other people with COVID. So the problem is, where are people's skills, particularly for developing high quality software? The two examples I showed you at the beginning of this talk weren't open source, so nobody was reviewing the code they were writing. And when you do get hold of the code, as I have done with Neil Ferguson's code, it's not documented, there doesn't seem to be any version control, there seem to be no requirements. Where is the oversight? Where is the help and training available for people to do better? Are they at the top right, SIL 4? Are they doing static analysis? Are they using formal methods and so on? I doubt it. And yet, lots of people have died from bad decisions about the pandemic. So here's the proposal. If you send a paper off to a medical journal, you have to have ethics approval from an ethics board. So if you're doing studies in a test tube, there aren't many ethics about it. But if you're doing studies on rats, you have to take more care. And if you're doing studies on humans, you have to take more care, and so on. And that's something we all accept and is routine. I think we should have something very similar, which I'm going to call a software engineering board. Every research institution should have one. And they help people doing research, which involves software, to do a thorough risk analysis and then act responsibly to the level of risk that their work is requiring. If they're just knocking up a computer game, that's SIL 0. But if they're developing software for ventilators or heart implants, then it's a SIL 3 or SIL 4. And then the software engineering board would say, can we help you do formal methods or better version control or whatever it is? So it's a straightforward idea. It needs a bit of work, but it means it's a way of helping people produce safer software. So moving forward, I've got papers and stuff and things that you can follow up. And you can get this talk off Christina later, so I won't dwell on this slide. But the question really is, what are your ideas for making more resilient open source hardware and software? There you go.
Fantastic, Harold. Thank you very much. Found that extremely interesting and relevant.